Okay, so good afternoon and welcome back. This topic is going to cover Ethernet switching basics. Ethernet switching basics. So we simply want to understand how data is forwarded at the data link layer, at layer 2. And the device that operates at the data link layer is the switch. In that video that we just watched, we watched a description of how the hub works. You saw how the hub forwards data. It simply has a shared medium. Then when it receives a frame, then everyone else receives that frame, right? In fact, if you looked keenly, you could have noticed that inside the hub, we simply have the bus topology. Is that correct? Is that correct? So really, we say that the hub operates at the physical layer because it does not maintain any record in order to reduce the broadcast domain or the collision domain. While on the other hand, the switch operates at the data link layer. And the router and layer 3 switches operate at the network layer or the internet layer of the TCP/IP protocol stack. Okay, so the forward. Data transmission on networks must comply with certain standards. Ethernet protocols define how data frames are transmitted over the Ethernet network. So Ethernet protocols. Understanding Ethernet protocols is the basis for fully understanding communication at the data link layer. So an Ethernet switch is the main device for implementing data link layer communication. It is essential to understand how an Ethernet switch works. So this course will describe the concepts related to Ethernet protocols, MAC address types, and working process and mechanisms of layer 2 switches. So that is what you're going to learn. By the end of this chapter, you should be able to. Dennis, please read out for us. By the end of this chapter, you should be able to.
You should be able to describe the basic concepts of an Ethernet network.
Yes.
Distinguish MAC address types. Get familiar with the working process of a layer 2 switch.
Yes.
Get familiar with the structure and generation process of a MAC address table.
Okay, thank you very much. So let's have an overview of the Ethernet protocols. Ethernet protocols. Okay, now earlier in earlier networks, so Ethernet is the most common communication protocol standard in local area networks. So when you're talking about a LAN, then most likely we're using Ethernet to communicate because it defines the cable types and the signal processing methods that are used on a LAN. Now, an Ethernet network is a broadcast network built based on the carrier sense multiple access collision with collision detection, CSMA CD mechanism. So we're going to tell you how CSMA CD works. Earlier Ethernet looked like that. Really, with the earlier Ethernet, it used the bus topology. It used the hub, whereby if this guy is sending data, if host A is placing data on the bus, then everyone else is going to receive that data. Everyone else will receive that data. Of course, only the person whose destination MAC address matches this particular frame is going to process it. Otherwise, the others are going to discard it. So for example, if A was sending to B, then C will discard it. This one will also discard it. But this one will process it. A few problems with this. Number one is the problem of collision. Collision means Collision means two machines send at the same time. So if that happens, data is going to get scrambled. It's going to collide, and it's going to get scrambled. When it gets scrambled, then the destination cannot be able to understand the meaning of that particular data. So that's one of the problems with this kind of arrangement. The other problem is also as the number of hosts continue to increase, then the number of broadcast packets become a concern, because now they're going to consume a lot of bandwidth. Because remember, every time A wants to send to a new device, they have to generate a broadcast packet, an ARP request packet. So if everyone is sending a broadcast, it increases the probability or the chances of collision occurring. That is number one. Number two, it consumes the bandwidth of the bus. So that was the main problem with this kind of Ethernet technology. So this was quickly replaced by having the star topology. The star topology now here, we have a switch interconnecting the hosts rather than a bus. The good thing with the switch, number one, is that it becomes easier to expand this kind of network because, number one, the switch provides many interfaces. And if we want to expand the network, we can simply connect to another switch, for example. So it becomes easier to scale. And this switch will maybe provide us again with 48 interfaces or ports. The other thing that this one does is that it separates the collision domains. We are going to see what collision domains are shortly. But generally, we've already agreed that when we send at the same time, we can be able. There's a chance that packets can collide because we are using a shared medium. But here, you see, we separate the collision domains. Sorry, we separate the collision domains. So with this kind of arrangement, we reduce the chances of collision ever occurring. The chances of collision ever occurring to each link, actually. And most of the time, on switching or switch networks, we use a medium that has lines that are specific for sending and others for receiving. So not same line for sending and receiving. Okay. So let's move on. That's just part of the introduction. So let's see what a collision domain is. So a collision domain is a set of nodes that are connected to the same shared medium. So we call that a collision domain. So all nodes in a collision domain compete for the same bandwidth. That is, packets sent by a node can be received by the other. That's the other problem. They compete for bandwidth, and packets can be received by other nodes. So it also becomes a security issue because if everyone is receiving your message and they can decide to open it up, so it's also a security issue. So with the earlier arrangement, you had a single collision domain. So the more devices you have in your network, then the higher the chances of collision occurring. So the other arrangement was to use the star topology by having a central device that will be able to send unicast frames or send from one device to another device, and thereby also separate collision domains. So by separating collision domains from a single one to multiple collision domains on each link, then we are able to reduce the chances of collision ever occurring. Especially now if we use a media here that use different lines for sending and receiving, then we totally eliminate the possibility or the chance of collision ever occurring. So okay. So on the earlier Ethernet network, they used a technology in order to reduce collision. They used a technology called CSMA-CD, or carrier sense multi-access, multiple access with collision detection, CSMA-CD. Now, in summary, CSMA-CD works like this. Listen before sending. Listen before sending. Number two, listen while sending. Listen while sending. Number three, stop sending if you detect collision. If you detect collision. Then number four, resend after random delay. Resend after random delay. So how does this work? Host A wants to send to host B. Host A wants to send to host B. So the first thing it will do is to listen. Listening is trying to detect whether the shared medium, which is the bus here, whether the shared medium is free or occupied. So if this shared medium is free, then it can be able to send. But even as it sends, it's still supposed to continue listening. But okay, the other option is while listening, you find that someone else is using the shared medium. So what do? You wait. You wait for a predetermined amount of time, then listen again. So that's what happens. But what if both of you listen at the same time? You listen at the same time, find no one is using the shared medium, then both of you send at the same time. What happens? Collision occurs. Collision occurs. So in order, again, to take care of that, that is why we have CD or collision detection. So we still have to keep on listening as we send. As we send, we have to listen. Now, in case collision occurs on the line, then the signals become unstable. The signals become unstable and the data is scrambled. So that's how computers are able to know that collision has occurred. So when you realize that collision has occurred, you have to stop sending. You have to stop sending. Then you have to wait for a random amount of time, then repeat the process again. That is, you listen. If no one is using, then you can start sending. So that is how carrier sense multiple access with collision detection works to reduce the chances of collision occurring or to resend data in case collision occurs. Carrier sense multiple access. It's on a shared medium. So that's how it works. Okay. So of course, I just want to reiterate that with switches, collision can only occur between individual interfaces. Are you seeing that? Between individual interfaces. We can only have collision here. And therefore, we totally reduce the chances of collision ever occurring. We only have the possibility of having a collision. So what we say is that with switches, they break one single. You see, this one gives us one collision domain, which makes scalability of such a network a big problem, because as the number of devices increase, the chances of collision also increase proportionally. Okay. So the other concept that is important is the concept of broadcast domain. Broadcast domain are also referred to as layer 2 broadcast domain because we know broadcast packets are never forwarded beyond layer 2. They're only forwarded within layer 2. So that's why they're called layer 2 broadcast domain. So a broadcast domain is when all hosts, ah, really, all hosts in the same broadcast domain can be able to receive what? Can be able to receive broadcast packets. So again, with the early Ethernet network, gives you one broadcast domain. Now the problem of broadcast domain is also not solved by the switch because the switch also creates a single broadcast domain. A single broadcast domain. How does it happen? If host A wants to send to host B, it will have to learn the MAC address of host B initially, and it will send an ARP broadcast packet. Now, how does the switch treat a broadcast packet? It's simply going to flood it to all other, send it out through all other interfaces other than the interface that received it. Any other switch will do the same. So everyone is going to get that particular packet. Now, when it comes to sending broadcast at layer 2, normally the destination MAC address is all ones, FFF, 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 FFF. Are they 6? Yes. So this is the broadcast MAC address, broadcast MAC address. So this will be the destination. Anytime you're sending a frame that you want to go to everyone, then the destination MAC address field is going to have all Fs. So I'm not sure whether I had talked about the MAC address earlier, media access control, but I'm sure you've even seen it on that video. So the MAC address is used to uniquely identify the network interface card. So each network interface card must have a unique MAC address. And each network interface card gives us a port or an interface, what we call an interface, or sometimes we call it a port. So this normally is provided by the network interface card, NIC, and the NIC will have a unique MAC address. So that is what we call a broadcast domain. So, okay, so here we're just looking at what is a network interface card. So the network interface card is a key component that connects a network device, such as a computer, a switch, or a router, to an external network. So normally, a computer will have a network interface card, and it will provide an RJ45 port or interface, which now can be connected. So it's called a network port, or a network interface, or simply as an interface or a port. So all those names are used to describe a network port. So NIC, each network port corresponds to a network interface card, as I said earlier. A computer or switch will forward their data through an NIC. So that is what we call an Ethernet NIC. Okay, so let's have a look at the frames, the Ethernet frame format. Ethernet frames are of two types. The first type is called Ethernet 2 frame. Ethernet 2 frame. Then we have another one that is called IEEE 802.3 frame. 802.3 frame. So those are the two types. So let's begin by exploring the Ethernet 2 format. So the first field here is the destination MAC address. Then we have the source MAC address. Then we have the type field. The type field performs a similar function as the protocol field on the IP header. So the type field will be able to specify the next protocol to which we are going to hand over this frame on the next layer. So it can be IP, it can be ARP, it can be it can be IP or ARP, the upper layer protocols. Are we together? Yeah, so that is what the type field stores. Then this is the user data. Then this is what we call the frame check sequence that is used for error checking and confirming the validity of the frame, that it has not been tampered with. FSC, frame check sequence. So it's on the data link layer that we add the Ethernet header and the Ethernet tail. So this is frame check sequence. Frame check sequence. So those are the fields of an Ethernet 2 frame. Now, the IEEE 802.3 Ethernet frame, quite similar up to here, and also similar here, user data and frame check sequence. But it adds a few other fields, like the length, which specifies the length of the Ethernet header. Then we have the LCC. LCC stands for the logical link control. The logical link control has what we call the destination service access point. DSUP. It also has what we call the source service access point. And lastly, it has the control field. The control field. So DSUP, this one is a SUP. DSUP is also used. DSUP is used as the type field of the Ethernet 2 in a similar way as the type field of the Ethernet 2 frame. So DSUP, destination service access point, on the IEEE 802.3 is used to specify the next protocol. So it can be IP, it can be ARP. So that is what it does. Okay. Then we have the snap. The snap is the snap field is subnetwork access protocol. So that is snap. So the snap field has several fields or subfields within it. The first one is the organizational code. Normally it's filled with all zeros. Then we have the type field. Again, this one performs the same function as the Ethernet 2 type field, Ethernet 2 frame type field. So that is really it. Now, normally these frames will have a size of between 64 bytes minimum to a maximum of 1518 to a maximum of 1518. And there's a reason. There's a reason why we have a minimum size. The reason as to why we have a minimum size is because, for example, you don't want the size of the frame to be so small, specifically because of how CSMA CD works. If it's too small, if the size of the frame is too small, that is below 64 bytes, if it's placed on the shared medium, it might be able to arrive to the destination. It might be able to arrive, or that particular host might finish sending the last bit, yet the first bit has not yet arrived to the destination. So we've sent the last, but the first one has not arrived. So what happens? What happens? What happens is that any other device can assume that the shared medium is free and therefore start sending. And when they do that, now collision will occur. So that's why we have a minimum size. That's why we have a minimum size. And now, this size of the frame also brings a very important concept called, is it minimum transmission unit? Transmission unit, or maximum, sorry. MTU, maximum transmit. Let me just call it transmit, MTU. So we talk of MTU when you're talking of the IP packets, and normally on an Ethernet interface, the MTU is 1500 bytes. 1500 bytes. So normally this 1500 translates to this 1518 bytes of the data frame. So don't forget that on an Ethernet interface, the maximum transmit unit normally is 1500 bytes. Okay. So what is a MAC address? What is a MAC address? MAC address is media access control. It is the address that uniquely identifies an NIC on a network. So each network interface card must have a globally unique MAC address. It has to be globally unique. It has to be globally unique, and it must comply to the IEEE 802 standard. So let's have a look. Let's have a look at how this. Yes, Maurice, you raised your hand.
Yeah, just wanted to confirm that MAC address cannot be changed.
Yes, very important. Thank you very much, Maurice. So you cannot change. You cannot change. Unlike the IP address, which is regularly changed, the MAC address cannot be changed. And that is just theoretical anyway. Okay. By saying that, I mean you can Google and find out how you can be able to change your MAC address. So these are some of the comparison between an IP address and a MAC address, which are important for you to understand. So on each Ethernet device, you must have a unique MAC address before you're able to send and receive data. And for you to assign the network, for you to access the network, you must have a unique IP address. So we have these two addresses that you must have. Characteristics of IP addresses within a network: can you have two devices with the same IP? No. Can you be able to change an IP address? Yes. IP addresses are also assigned based on the network topology. Most of the time, we create subnets. You remember subnets? Characteristic of MAC addresses: they're also unique, cannot be changed, and you're going to understand why in the subsequent slides. And MAC addresses are assigned based on the manufacturer. Based on the manufacturer. Based on the manufacturer. So as you can see, every NIC will have a unique MAC address, and every machine will have a unique IP on the network. Can a network have either a MAC address or an IP address? Just either, but not both of them. Fritz? Can a network device have either MAC address or an IP address? You think it has to have both? Why? Because the MAC address comes with the device. So just with the MAC address, do you think the device can be able to send data, even just at layer 2? Do you think just with the MAC address, the device can be able to send data on the network? Yes. Okay. Yes, Luyo? Oh, you think it should have both? You know, okay. Why? Yes? Very true. Very true. Yeah, so I think Luyo is just mentioning the fact that we already know how the data moves from layer to layer, right? And therefore, what then happens at layer 3 if we don't have an IP address? And we know the purpose and the functionalities of layer 3. So this end-to-end delivery of the data to the destination, how will it happen without an IP address? Again, how do computers or hosts on a network learn about the MAC addresses of their counterparts? Through which protocol? ARP, right? Right? Through ARP. Can ARP work without an IP address? Huh? It cannot work without an IP address. Okay. So the media access control uniquely identifies NIC on a network. Each NIC must have a globally unique address. Did I go back or forward really? Oh, sorry. Okay, so this is the format of a MAC address. Normally, the MAC address is made up of 48 bits, written in groups of 6 bytes. Written in groups of 6 bytes. So this is how it's written. That's binary, sorry. Oh, sorry, not written in groups of 6 bytes. I'm very sorry. In total, 48 bits in total is what? 6 bytes, right? Yeah, and normally in binary, it is written in groups of 8 bits, 8 bits, 8 bits, 8 bits. So another numbering format is here. This numbering format is called hexadecimal. Most of the time, MAC addresses are written in hexadecimal. So 00IE or maybe 10DDDD02. So when you have time, you can learn how to convert between hexa to binary and vice. and vice versa. But normally that is how we write MAC addresses. And between each group, between each of the 6 groups, we can separate them using hyphens, like what we've used here. We've used hyphens, or we can use colons, or we can write them without any separator. But the most common format is by using hyphens. So the MAC address composition and classification, the MAC address is made up of 2 parts. The very first part of the MAC address is called an organizational unique identifier. Organizational unique identifier. So the first 24 bits of the MAC address is a number that is globally unique and is assigned to the vendor or the manufacturer of the NIC by IEEE. So it's globally unique. So you have to purchase that particular number. Then the remaining 24 bits is what we call the company ID. The company ID is assigned by the manufacturer uniquely and incrementally. So 1, 2, 3, 4, 5, 6, 7. So that's how we are able to say that by design, the MAC address has to be globally unique. Has to be globally what? Unique. Now, we have 3 MAC addresses classification. 3 MAC address classification. The first one is called unicast. You remember unicast messages? Simply means we are going to be sending one-to-one messages. Then this one-to-many, right? Multicast, broadcast, one-to-all, right? We already met broadcast, you remember? We said that when a message is a broadcast message on layer 2, then the destination MAC address is all Fs. All Fs if converted to binary, it's going to be all ones. Are you seeing that? Okay. Now let me show you. How do you identify that the MAC address is a unicast MAC address or a multicast MAC address? Please remember that you're going to find this in the exam. For a unicast MAC address, the first bit, not really. Is it the 8th bit? Is it the first or the 8th? This one. This bit here. Which position is this? So that particular that particular bit will always be a 0. Will always be a what? 0. So the first bit of the first octet, will be a 0. On the other hand, for a multicast, other than a broadcast that has all ones, the first bit of the first octet, will always be a 1. So that's how you can easily be able to distinguish. That's how you can be able to distinguish between a unicast MAC address and a broadcast and a multicast MAC address. Anyone with a question? Okay. So the other thing you need to know, unicast MAC address. Unicast MAC address can be used as the source or destination address. Are we together? Unicast MAC address can be used as the source or destination address. What do you think about the multicast MAC address? Can a multicast MAC address be used as the source MAC address? Remember, we said multicast MAC address is 1 to, or multicast message is 1 to many. So can a multicast MAC address be used as a source MAC address? Can only be used as a destination MAC address. What about broadcast? 1 to all? Can it be used as a source MAC address? Huh? Cannot be used. Cannot be used. Now, in case two terminals have the same MAC address on the same network, then communication is going to fail. The two machines are not going to be able to communicate, and they may also not be able to communicate with other devices. So as I said, if you Google around, you can be able to see how you can be able to change the MAC address of your NIC to use a temporary one, for example. So in case two of you in the same network segment have the same MAC address, you cannot be able to communicate. So also remember that. Okay. Oh, so this is a unicast frame, unicast Ethernet frame with a unicast Ethernet frame, one device sends to, places it on the shared medium. These ones are also going to receive it, but only this one is going to process it. The other ones are going to drop it. Why? Because the destination MAC address is for host B, 02 is for host B. So you can see that this bit for a unicast MAC address, that bit of the first octet or byte is going to be a 0 because it's a unicast. Okay. So broadcast 1 to all. So everyone is going to process. Host A sends with destination MAC of all Fs, places it on the shared medium, everyone processes it. Everyone opens the message. Open, open, open. Broadcast. Then we have multicast. Multicast is 1 to a group. So multicast is used to decrease the bandwidth utilization that is caused, for example, by broadcast. So we've already seen one application of multicast. We talked of OSPF using a multicast address. So that we don't send to everyone. We only send to people who are communicating via OSPF. So multicast is 1 to a group. So for example, here, we place the multicast packet here. This one is not in that group, therefore drops that particular frame. This one opens it up. This one opens it up. So again, just to emphasize, that bit of the first octet will always be a 1 for multicast MAC address. So let's see how the switch works. We begin by having an overview of a typical architecture of the campus network. So as we know, the campus network normally will adapt the multi-layer architecture. At the very bottom of the layer, we have the access layer. The access layer will normally have the layer 2 switches that provide access to the end devices, to the hosts. Aggregation layer, we might use here the layer 3 devices that now will enable inter-network communication between the access devices. Then core layer then egress layer that connects us to the internet. So at this particular point, our focus really is to understand how communication occurs. How communication occurs where? At the access layer. And which devices enable that? Layer 2. Layer 2 switches. These are layer 2 switches. So we use layer 2 switches. We don't use layer 3 switches for access layer. Okay. So these switches are also referred to as what? Layer 2 Ethernet switches. So as I said again, they are the ones that are closest to the end users and are used to provide connectivity to the end user devices. So why we call them layer 2? Because they work at the data link layer of the TCP/IP model. And therefore, they forward data. They forward data based on what? Based on the MAC address. Based on the MAC address. Do we also have layer 3 switches? Do you also have layer 3 switches?
Yes.
Okay. So why do you think we need layer 3 switches, yet already we have routers? Why do you think we need layer 3 switches, yet we already have routers? Anyone? Yes. Yes, Kellen? They speed up their forwarding. Okay, very good, very good, very good. So forwarding performance. Okay. Another one. So routers are also quite expensive, and they have low interface quantities. So for this reason, for the aggregation layer, core layer, sometimes we use layer 3 switches. Layer 3 switches. So right now, we won't really go deep into explaining what forwarding performance is, but just know that the method that switches use to forward data is quite faster compared to routers. So this one will have better forwarding performance. Then cheaper compared to router. Number 3, high number of interfaces. So that's why we need to use layer 3 switches. See, last week I showed you a router. How many interfaces did it have? How many? 4. Was it 6? So you see, if you use that at the aggregation layer, it means your network cannot be able to expand very much, right? But if you use a layer 3 switch, gives you 12 interfaces or 24 interfaces or even 48, means your network can be able to grow further, right? Yeah, so that's why at the aggregation layer or even the core layer, we use layer 3 switches for these reasons. So I hope you understand that. It's very important. Okay, so let's see how switches work. So as we've said, switches operate at the data link layer, thereby forwarding data based on the MAC address. Based on the MAC address. The switch will also break or isolate collision domains. It isolates collision domains. So collision can only be able to occur here. Unlike the bus topology, the early Ethernet networks where they were sharing the same bus. So here, no. So normally, when we say it forwards using the MAC address, we are going to understand better how that happens. But what you need to know is that the switch maintains what we call a MAC address table. Here, MAC address table. So if this guy, host 1, is sending a frame to host 2, then it will have the source and destination MAC address. So source and destination MAC address. It will also have the IP header. So after receiving the frame, the switch will learn the source MAC address of the frame and search the MAC address table for the destination MAC address of this guy number 2 of the frame and forward the frame through the corresponding interface. What that means is this: you send the frame, the switch receives it, checks its MAC address table. MAC address table is used to save an association between the MAC address of a device and the switch interface to which it has been connected to. So that's how, if it finds your MAC address, it checks the destination MAC address on the message, checks its table. If it finds that same MAC address in the table, then reads the outgoing interface, then sends that frame just out through that interface and not through all the interfaces. So in summary, that is how it works. But we are now going to understand it in detail, bit by bit. So the MAC address table, as we have said, is used to map the MAC address of a particular device to the switch interface, that it has been connected to. So the table looks exactly like this, with these columns at minimum, the MAC address and the interface. Then you have MAC1 has been connected to this. MAC2 has been connected to G002. And therefore, if a frame comes, I check the destination MAC address is MAC2. I simply forward out that packet through this interface only, G002. I don't send it out to G003 because it's a unicast. It's a unicast frame. So a switch can do one of 3 things to a frame that it receives. The very first thing it can do is flooding. A switch will flood frames in one of 2 instances. A switch will flood frames in one of 2 instances. The first one, if it's a broadcast. Are we together? Number 2, if it's unicast and MAC address is not in my MAC table. So flooding simply means send it out through all the other ports other than the port that received that particular frame. So I have 4 ports, port 1, port 2, port 3, port 4. I receive a broadcast packet on port 1. I'll send it out through port 3, port 2, and port 4. So send it out through all the other ports other than the port that received that frame. Number 2, if I receive a frame, check through my MAC address table and I don't find the destination MAC address in my MAC address table, then I'll simply flood it. I'll send it out through all the other ports other than the port that received that particular frame. So those are the 2 instances which we are going to be doing flooding. The other thing that the switch can do other than flooding is forwarding. So forwarding is we receive a frame, we check our MAC address table, we find, oh, the MAC address of host 2 is there, MAC 2. So it's connected to G002. So we just send it out through G002. So that's what we call forwarding. And the last one is what we call discarding. So I'm going to describe discarding in the subsequent slide. So discarding is simply dropping that frame, just drop it. Okay, so I think I have already described this. I have already described flooding. We've said if number one, 2 instances. One, we send a frame destination MAC address MAC 2, but in our own MAC address table, we don't have MAC 2. So we just send it out through all the interfaces, G003, G002, like that. So that's the first instance where we do flooding. Number 2 is if the destination MAC address is all Fs. So meaning it's a broadcast. Forwarding host 1 wants to send a frame to host 2, so the destination MAC address will be MAC 2. Switch receives it, checks the MAC address table, finds, oh, MAC 2 is here. So if MAC 2 is here, let me send this frame out through this one only, through this interface only, and therefore it will send it out through that interface only. So that's what we call forwarding. And lastly, we have discarding. Okay, so here, host 1 wants to send to host 2, and therefore the destination MAC address is going to be host 2's MAC address. Now, this switch 1, receives that particular packet frame. Switch 1 then searches its own MAC address table for the destination MAC address of the frame. So if the destination MAC address does not exist in this particular table, then switch 1 will flood it. Switch 1 will flood it. I don't know why they put it here, because I thought it was not supposed to be found. But anyway, just understand that in this case, we have looked here, and we have not found the MAC address of host 2. So what do? We flood it. So we flood and we flood. But when we flood, we're also flooding to switch 2. So what will switch 2 do? So switch 2, so here, the switch finds the destination MAC address of the frame in the MAC address table, but the interface number in the table is the number of the interface through which the frame enters the switch over the transmission medium. So in this case, the switch discards the unicast frame. Sijui kama mmeelewa. Oh, sorry. I know where I went wrong. I confused something. Let me begin again. So host 1 wants to send to host 2. So the destination MAC address is that comes here. This one checks its own MAC address table. I don't have MAC address of host 2 or MAC 2. I don't have that MAC address. So it floods, right? Are you together? It floods. As it floods, this one goes in through switch 2. It goes into switch 2 through which interface? G001. Are we together? So what happens is this. Switch 2 then checks its own MAC address table. That is what is happening here. It is switch 2's table. It's not switch 1. I had confused. So this is switch 2's table. So it checks, and then it finds MAC address of 2, right? But now finds out that, hey, the interface through which I'm supposed to forward this packet is G001. But G001 is the same interface that received this frame. Are we together? Meaning this frame has already reached its destination. So we cannot send it out through the same interface. So we simply do what? Discard it. So is that clear? Yeah. Okay. We discard it. Okay, so let's look at the process the process by which the switch learns MAC addresses. Initially, please note that initially, at the initial stage, the MAC address table of the switch is what? Is empty, meaning we do not have any. We do not have any MAC address. Then what happens? Host A sends a frame to host 2. Host 1 sends a frame to host 2. So it will have the source MAC address. It will have the source MAC address. So here, the assumption is that host 1 already knows the destination MAC address, which is this one, right? We already know it. Okay, so after the frame is received on the switch G001, the switch searches the MAC address table for the destination MAC address of the frame. Will it find it? It's still empty, so nothing. So if no matching entry is found, the switch considers the frame as it's called an unknown unicast frame. It is an unknown unicast frame that is flooded. An unknown unicast frame. So that is what happens there. In the next step, what happens? The switch then reads the source MAC address of host 1 and updates its table. It updates its table. So it will update its table with the MAC address of host 1 and the interface via which it has been connected. After that, it will do what? It will flood that particular frame through all the interfaces other than the interface that received that particular frame. Are you together? So process number 1, by the way, is flooding. You flood that unknown unicast frame, then you update your MAC address table. You make a MAC address entry with the MAC address of host 1 and the interface via which it has been connected, which is G001. So the frame is also received by the host connected to other interfaces on the switch. These hosts, however, will discard the frame. So we know that. So host 2 receives and processes the frame, responds to host 1, and sends the frame to the switch. So host 2 has received it, then it creates a reply. It creates a reply. Okay, so let's find out what happens. What happens when the switch receives the reply from host 2, what do you think will happen? So here, if the switch finds the corresponding entry in the MAC address table, then the switch will forward the unicast frame through G0001. At the same time, the switch will update its MAC address table and create a corresponding MAC address entry and associate it with G002 for host 2. Is that clear? Okay, so that is how the switch operates in order to be able to learn MAC addresses and in order to be able to forward a unicast frames to the individuals rather than to everyone. So let's look at the process of data communication within a network segment. So the scenario here is host 1 wants to access host 2. So that is the task. So the host is in the initialized state. So it means it only knows the IP address, its own IP address and MAC address. But we have been told to assume that the IP address of the peer host has been obtained. So this guy wants to talk to host 2, but we only have the IP address of host 2. So the switch is also on the initialized state. It has just been powered on, meaning the NINI is empty. The table is empty. So what is going to happen? How will host 1 learn about the MAC address, destination MAC address? What is it going to do? What is it going to do? To learn the MAC address of host 2. Okay. MAC address table entry. Something I forgot to mention and is very important. The MAC address table entry, that is the association between the MAC address and the interface via which it has been connected to. It has something we call the lifespan. The lifespan. This lifespan is also called the aging time. Aging time. In Huawei S series switches, the default aging time for MAC address entries is 300 seconds. This means that if within 5 minutes we have not received any frame whose MAC address is that, then we delete that entry. Are we together? We delete that entry from the MAC address table. Now, that is just one instance in which the MAC address entry is deleted. The other instance is when you disconnect a device. When you disconnect a device from a switch interface, then the switch will detect that the interface status, physical status, has transitioned from up to down. And therefore, it's going to go to its MAC address table, find any entry associated with that particular interface number, and delete it. So those are the two instances. Two instances within which the switch can be able to delete the MAC address table entry. MAC address table entry can be learned dynamically, like what we've demonstrated is dynamically, or it can be learned statically. Statically is manually configured. Sorry. Okay. Yes, Maurice, just go ahead.
Yeah, thank you, teacher. Just wanted to know the cycle at which the device, the hosts on the network normally take to periodically check or rather learn the MAC addresses on the network. Come up again. Just want to know how long, in terms of minutes time, how often do they periodically check to learn the MAC addresses, the equipment? You talked of 300 seconds, is it? Is that the case?
Yeah,
Every 300 seconds?
This 300 seconds is the amount of time the MAC address. You see, in the MAC table, we are going to say MAC2, that is the MAC address of host 2, is associated with GE0/0/2. Are you getting the point? So if we don't receive any frame within 300 seconds coming from this source, MAC2, then we delete this entry from the MAC address table.
Okay.
And that is what we call the lifespan of a MAC address table entry, or the aging time. So the aging time is 300 seconds. So we're talking about the switch here, not the end device. We know the end devices also have a table called the ARP cache table, right?
Yeah.
Yeah. So the ARP cache table, as we saw in the lab the other day, is also has an aging time, right? Yeah, I'm not sure how long the aging time is, but for the switch MAC address table entry, it is 300 seconds for Huawei S-series switches.
Fine. Thank you. Thank you, teacher.
Okay, thank you very much. Okay. So the data encapsulation process for that scenario that we have just looked at, so before we send, of course, the data has to be encapsulated from the very top layers to the bottom. Specifically at the data link layer, we are going to add an Ethernet header and a tail. So information that needs to be encapsulated on the Ethernet header, for example, include the source MAC address and destination MAC address. Then the tail contains the frame check sequence. So initially, host 1, before sending, it's going to check the ARP cache table, its local ARP cache table. Do I have an association between this IP address? Because right now, the only thing it has is the MAC address, the IP address of host 2. So do I have the IP address of host 2 and the MAC address in my ARP cache table? So it will check. But because they've not communicated before, then it's going to find that it's empty. So I don't have that association. Similarly, this guy, the switch, the MAC address table is also empty. This is the command for displaying the contents of the MAC address of a switch. Display MAC-address, and then you can enter the optional command there, verbose. So it's going to give you the port number and the type and the MAC address. How it learned it, statically or dynamically, that is the type and the MAC address. Okay, so next, host 1 is going to send a what? Host 1 is going to send a what? ARP request packet, right? ARP request packet. Then what happens when the switch receives this particular packet? What happens? The switch will check its own. It will check its own what? MAC address table. But the switch will also read the destination MAC address, which is OLEFs. And therefore, it's going to send out this message through all the interfaces other than the interface that received it. So everyone is going to receive this ARP request because it's a broadcast message. It's going to be flooded. Other than that, after flooding, the switch is going to do what? It's going to update its MAC address table. With what? With the MAC. It's going to check the source MAC address. So with the MAC address of host 1 and the interface via which it has been connected to. So you can see the interface it has been connected to, host 1, is G001. The type, how did we learn about this? Dynamic. Okay. The other day during the lab, of course, we explored. We explored the ARP header. You remember? Huh? And we know, for example, what the operation type is, opcode. And the destination MAC address of the request is normally all zeros because we don't know the destination MAC address. It's normally all zeros. Okay. So the next thing is that host 2 will reply. So host 1 has asked who has 192.168.1.2. Then host 2 will reply, I have it, and also reply with its MAC address as the source MAC address. We're gonna reply with its source MAC address, and of course, on the Ethernet header, it's also going to indicate its own MAC address. The switch receives that, then updates that MAC address and the interface via which it has been connected, and say that it has learned it dynamically. So that's what the switch will do, update its MAC address table. After that, the switch searches through, looks at the destination MAC address, then searches through its own table, finds that this guy is here. If I want to reach this guy, I send it out through this port. And therefore, this message is going to be sent out through that port, G001. And thereby, that port is going to, that message is going to get to host 1. So that is the data communication process at the data link layer. Anyone with a question or comment? Question or comment? Okay, thank you very much. Thank you very much. Okay, so we have these 2 questions. I give you some time to discuss them. Please have a look at them. Next week, we will begin, I think, with looking at VLANs. Then we can do the lab on Ethernet switching and VLANs. So thank you very much for your time, for your participation. Asanteni sana.